Black holes are among the most mysterious objects in the universe, with gravitational forces so strong that nothing, not even light, can escape once it crosses a critical boundary known as the event horizon. This boundary marks the edge of a black hole, a place where space and time are stretched to their limits. While the interior of a black hole remains hidden from view, the region near its edge is where some of the most extreme and fascinating physics occurs. The event horizon is not a solid surface, but rather an invisible boundary that separates the black hole from the rest of the universe. Anything that crosses this line is pulled inevitably toward the singularity, where all known laws of physics break down. However, the effects of a black hole can be seen and studied from just outside the event horizon, where intense gravitational forces distort light, stretch matter, and even create bizarre quantum effects. Studying what happens at the edge of a black hole could unlock some of the deepest secrets of the universe, from spaghettification, the stretching of objects due to extreme tidal forces, to Hawking radiation, a mysterious quantum process that suggests black holes slowly evaporate. The event horizon is a place where physics is pushed to its limits. Scientists are still grappling with questions about whether information is truly lost in a black hole, and whether new theories of quantum gravity might reveal hidden pathways out. With recent breakthroughs like the first ever image of a black hole captured by the Event Horizon Telescope, we are closer than ever to understanding what happens at the very edge of these cosmic monsters. Exploring the mysteries of black hole boundaries may not only help us understand these enigmatic objects, but also challenge our fundamental understanding of space, time, and reality itself. The event horizon is the defining boundary of a black hole. It is not a physical surface, but rather an invisible limit in space where gravity becomes so overwhelming that nothing, no matter, no light and no information can escape once it crosses over. This boundary represents the ultimate one-way door of the universe, separating the known from the unknowable. In simple terms, the event horizon is the region where escape velocity, the speed required to break free from the black hole's gravitational pull, exceeds the speed of light. Since nothing can travel faster than light, anything that crosses the event horizon is effectively cut off from the outside universe. From a distance, the event horizon appears as a dark, spherical shadow against the backdrop of space. This dark region is what astronomers captured in the first ever image of a black hole, taken by the Event Horizon Telescope in 2019. Although the black hole itself is invisible, the glowing ring of superheated gas and light bending around it allows us to infer its presence. How gravity warps space and time. As an object approaches the event horizon, the effects of gravity become increasingly extreme. According to Einstein's theory of general relativity, gravity is not just a force, but a curvature of space-time. A black hole's immense gravitational pull creates an extreme warp in space-time, causing time to slow dramatically for an object falling toward the event horizon. To an outside observer, an object nearing the event horizon would appear to move more and more slowly, never quite crossing the boundary. This happens because time dilation, the slowing of time due to gravity, becomes infinite at the event horizon. However, from the falling object's own perspective, it would cross the event horizon without noticing anything unusual at that exact moment. What happens when an object approaches? An object falling toward the event horizon would experience increasing gravitational forces, especially if it were an extended body rather than a single point of mass. The immense tidal forces at play, caused by the difference in gravitational pull between the object's near and far sides, lead to a process known as spaghettification. If the black hole is small, the tidal forces become so strong near the event horizon that any object, whether a spaceship, an astronaut, or even a planet, would be stretched into a thin, elongated shape like a noodle. However, if the black hole is supermassive, such as the ones at the centers of galaxies, the event horizon is so large that an object could cross it without immediate stretching, only feeling the extreme gravitational pull much later on its journey toward the singularity. The event horizon marks the ultimate limit of knowledge. No signals, no messages, and no information from beyond this boundary can ever reach us. However, just outside the event horizon, fascinating processes occur, such as the emission of Hawking radiation, which suggests that black holes may not be completely inescapable after all. Spaghettification, the fate of falling objects. As an object drifts closer to the event horizon of a black hole, the gravitational forces acting upon it become increasingly intense. This effect is especially pronounced in smaller black holes, where the difference in gravity between the object's top and bottom, known as tidal forces, grows exponentially. Eventually, this leads to one of the most dramatic and violent phenomena in astrophysics: spaghettification. Tidal forces are caused by the difference in gravitational pull on different parts of an object. In everyday life, we experience a mild version of this effect with Earth's tides, which occur because the Moon's gravity pulls more strongly on the side of Earth closer to it than on the far side. Near a black hole, however, this force becomes extreme. As an object falls feet first into a black hole, for example, the gravitational pull on its feet is significantly stronger than the pull on its head. This difference stretches the object lengthwise while simultaneously compressing it sideways, creating a long, thin shape, just like a strand of spaghetti. In small to medium-sized black holes, spaghettification happens well before an object even reaches the event horizon. The stretching force grows so powerful that it physically rips apart molecules, atoms, and even subatomic particles. Anything falling in is reduced to a stream of energy and fundamental particles before it ever reaches the singularity. For example, if an astronaut were unfortunate enough to fall into a stellar mass black hole, they would be stretched and torn apart long before crossing the event horizon. From an outside observer's point of view, they would appear to slow down as they approach the event horizon, their image fading and redshifting due to gravitational time dilation. However, from their own perspective, they would be elongated and torn apart within seconds. Differences for small versus supermassive black holes. While spaghettification is inevitable in smaller black holes, it may not happen immediately in supermassive black holes, such as those found at the centers of galaxies. These black holes have much larger event horizons, and the tidal forces at the boundary are weaker. This means that an object, or even a person, could technically cross the event horizon without immediately being torn apart. However, this doesn't mean survival. The object would still be pulled toward the singularity at the black hole's center, where tidal forces eventually become overwhelming. No matter how large the black hole, the end result is always the same: total destruction within the depths of the singularity, where space and time cease to have any meaning as we understand them. Despite this grim fate, black holes may not be perfect cosmic prisons. Theories like Hawking radiation suggest that black holes slowly lose mass over time, raising the question of whether some form of energy or information might escape after all. For a long time, black holes were thought to be inescapable cosmic traps, consuming everything that crossed their event horizon without releasing anything back into the universe. However, in 1974, physicist Stephen Hawking proposed a groundbreaking idea. Black holes are not completely black. Instead, they emit a faint radiation, now known as Hawking radiation, which suggests that black holes might eventually evaporate over time. Hawking radiation arises from the strange and counterintuitive laws of quantum mechanics. In empty space, tiny pairs of virtual particles are constantly popping in and out of existence. Normally, these pairs annihilate each other instantly and disappear. But near the event horizon of a black hole, something different happens. If one particle of the pair falls into the black hole while the other escapes, the black hole loses a tiny amount of its mass. Over immense timescales, this process causes the black hole to gradually shrink and lose energy. The smaller the black hole becomes, the faster it radiates until it eventually disappears in a final burst of high-energy radiation. Hawking's discovery was a major breakthrough because it linked quantum mechanics and general relativity, two fundamental but often conflicting theories of physics. It suggested that black holes are not completely sealed off from the rest of the universe but are instead slowly leaking energy. However, this raises profound questions. What happens to the information about everything the black hole swallowed? According to quantum mechanics, information can never be truly destroyed. But if Hawking radiation carries away energy without preserving any information, this leads to the black hole information paradox, one of the biggest unsolved mysteries in physics. If black holes emit radiation, does that mean they are not entirely cut off from the universe? Some theories suggest that information about everything a black hole has consumed is encoded in the radiation it emits, though in a highly scrambled form. Others propose even more radical ideas. Some physicists argue that black holes might not truly destroy information, but instead store it on their event horizons, acting like a vast cosmic hologram. This idea, known as the holographic principle, could reshape our understanding of reality itself. While no one has directly observed Hawking radiation, since it is far too weak to detect from existing black holes, future advances in technology might provide new insights. If we could confirm the existence of Hawking radiation, it would not only validate one of the greatest theoretical predictions in modern physics, but also open new doors to understanding the nature of black holes and the fate of everything that falls inside. The information paradox is anything truly lost. One of the greatest mysteries in modern physics is the black hole information paradox, a deep conflict between quantum mechanics and general relativity. According to classical physics, anything that crosses the event horizon is lost forever, consumed by the singularity at the black hole's core. However, quantum mechanics states that information can never be truly destroyed. This contradiction has puzzled scientists for decades, leading to new theories about the nature of black holes and reality itself. If information were truly lost inside a black hole, it would break the fundamental rules of quantum physics, which dictate that information about a system's past must always be preserved in some form. Yet, Hawking radiation, the slow emission of energy from black holes, appears to carry no trace of the information from the matter that originally fell in. If black holes evaporate completely over time, where does that information go? Does it simply vanish, violating quantum laws, or is there a hidden mechanism that allows it to escape? One possible solution to the paradox is the holographic principle, which suggests that all the information about a black hole's interior is encoded on its event horizon, like a cosmic hologram. In this view, information is not lost, but rather stored in a two-dimensional surface, much like a movie projector encoding a three-dimensional image on a flat screen. This idea has led some physicists to propose that reality itself may be fundamentally holographic, with the three-dimensional universe we experience being a projection of deeper quantum information. Another hypothesis is that black holes do not actually destroy information, but instead release it in a scrambled form through Hawking radiation. Some scientists believe that as black holes evaporate, their radiation subtly encodes information about everything that was once inside them. If true, this would mean that black holes are not cosmic erasers, but rather highly complex information processing objects. More radical theories suggest that black holes might act as tunnels to other regions of space-time or even other universes. If information is not lost, but rather transported elsewhere, it could mean that black holes are not endpoints of destruction, but instead doorways to unknown realms. Despite these fascinating ideas, the black hole information paradox remains unresolved. Future discoveries in quantum gravity, new observations of black holes, and advances in theoretical physics may one day provide a solution. Until then, the paradox challenges our deepest assumptions about space, time, and the very fabric of reality. For centuries, black holes existed only as theoretical objects, predicted by Einstein's general relativity, but beyond the reach of direct observation. However, recent breakthroughs have allowed scientists to peer closer than ever before to the event horizon, the mysterious boundary where space and time are stretched to their limits. By studying the light, matter, and energy that swirl around a black hole's edge, astronomers can unlock new insights into these cosmic giants. The most groundbreaking achievement in black hole research came in 2019 when the Event Horizon Telescope, or EHT, captured the first ever image of a black hole's event horizon. This historic image showed a glowing ring of superheated gas surrounding a dark circular shadow, the silhouette of a black hole. The EHT used a global network of radio telescopes to achieve the resolution necessary to see this distant object. Located in the galaxy M87, over 55 million light-years away. This observation confirmed long-standing predictions about how light bends around a black hole and provided direct visual evidence of event horizons. Beyond images, scientists study black holes by examining the behavior of matter near their edges. As gas and dust spiral inward, they form an accretion disk, a swirling ring of plasma that emits intense radiation. These disks can glow brightly in X-ray and radio wavelengths, making them detectable by space telescopes like Chandra and XMM Newton. The movements of this matter provide clues about the black hole's mass, spin, and effects on surrounding space-time. Another key area of study is relativistic jets, narrow streams of high-energy particles ejected at nearly the speed of light from the poles of some black holes. These jets, powered by the black hole's rotation and magnetic fields, can extend for thousands of light-years and influence the evolution of entire galaxies. By analyzing these jets, astronomers gain insights into the complex interactions between black holes and their environments. The next frontier in black hole research involves gravitational wave astronomy, pioneered by observatories like LIGO and Virgo. When black holes merge, they send ripples through space-time, allowing scientists to detect their presence even when no light escapes. These waves provide a new way to study black holes and test fundamental theories of gravity. Future missions, such as the proposed LISA, or Laser Interferometer Space Antenna, will take gravitational wave detection into space, offering an even clearer view of black hole collisions and interactions. Meanwhile, advancements in telescope technology, like next-generation radio arrays and space-based X-ray observatories, will continue to push the boundaries of what we can observe at a black hole's edge. Despite these achievements, many mysteries remain. What truly happens at the event horizon? Is information preserved or lost? Could hidden physics beyond Einstein's theory of relativity be at play? As technology advances, our understanding of black holes will only deepen, bringing us closer to answering some of the most profound questions about the universe. Could we ever survive a journey to a black hole? The idea of traveling to a black hole has long fascinated scientists and science fiction writers alike, but could a human or even a spacecraft ever survive such a journey? While the laws of physics suggest that crossing the event horizon is a one-way trip, the experience of falling into a black hole depends on the size of the black hole, the speed of descent, and the forces acting upon the traveler. For a small, stellar mass black hole, the outcome is almost certainly fatal. As an object falls toward the event horizon, it encounters immense tidal forces, differences in gravitational pull between its top and bottom. This stretching effect, known as spaghettification, would rip apart any spacecraft, astronaut, or even individual atoms long before reaching the horizon. No material, no matter how strong, could withstand such extreme forces. However, for a supermassive black hole, like the one at the center of the Milky Way Sagittarius A*, the situation might be different. The event horizon of a supermassive black hole is much farther from its singularity, meaning the gravitational gradient is weaker at the boundary. A person or spacecraft could, in theory, cross the event horizon without immediately experiencing spaghettification. From their perspective, they would see the universe outside gradually fade as they drift deeper into the black hole's interior. But surviving the crossing does not mean escape is possible. Once inside, the laws of physics dictate that all paths lead to the singularity. a point of infinite density where space and time break down. No known force can resist this inward pull. The journey would be one of no return, and what happens at the singularity remains unknown. Perhaps the traveller would be crushed out of existence, or perhaps something even stranger, like quantum effects or hidden dimensions, would come into play. Some speculative theories suggest that black holes could be gateways to other parts of the universe, or even wormholes to entirely new realms of space-time. If true, a carefully navigated black hole entry might not mean destruction, but instead a passage to somewhere else. However, no evidence currently supports this idea, and the intense energy conditions near singularities make such travel purely hypothetical. Even if we could somehow avoid destruction, another major obstacle remains: communication. Due to gravitational time dilation, an observer outside would see a falling object slow down as it neared the event horizon, appearing to freeze just before crossing. Meanwhile, the traveller would experience time normally, but would never be able to send messages back to the outside universe once past the horizon. While black holes remain the ultimate death traps in classical physics, future breakthroughs in quantum gravity, wormhole theories, or even exotic matter physics could one day change our understanding. For now, however, any journey into a black hole would be a one-way ticket into the unknown. Black holes remain among the most mysterious and awe-inspiring objects in the universe. From the mind-bending effects at their event horizons to the paradoxes surrounding information loss, these cosmic giants challenge our understanding of space, time, and reality itself. The discovery of Hawking radiation suggests that black holes may not be eternal, while breakthroughs in gravitational wave detection and direct imaging have given us an unprecedented view of these extreme environments. Despite our progress, many fundamental questions remain unanswered. Does information truly escape from black holes, or is it lost forever? Could black holes be portals to other parts of the universe? And what really happens beyond the event horizon? Theories like the holographic principle, quantum gravity, and even wormholes offer tantalizing possibilities, but we are still far from definitive answers. Future advancements in astrophysics, quantum mechanics, and space exploration may one day unlock these secrets. As telescopes improve and new technologies emerge, we might witness the next great revolution in our understanding of black holes. Until then, they remain cosmic enigmas, both terrifying and beautiful, defying the limits of our knowledge and inviting us to explore the edge of the unknown.